Hello, everyone. I'm Dr. NAVNEET KAUR, Associate Professor in Department of Electronics and Communication Engineering, SIRT College, Bhopal. Today, I'm taking lecture of subject Signals and Systems. In my previous lecture, I have already discussed basic concepts of the Z transform. Now, in this lecture, I'll be taking properties of the Z transform. Now, to start with the first property of the Z transform, which is linearity property. Now, according to the linearity property, if x1n is having Z transform x1z and x2n is having Z transform x2z, then if I want to find out the Z transform of A1 x1n plus A2 x2n, it will be A1 x1z plus A2 x2z. That means if two signals are multiplied by constants A1 and A2 and are added, then their Z transform will also be multiplied by same constants A1 and A2 and both will be added. Now we will go to the proof of this property. Now I'll start with the basic formula of xz, which is summation n is equal to minus infinity to plus infinity xn z raised to the minus n. Now in this property, xn is a1 x1n plus a2 x2n. That means this is the signal for which I want to find out the z transform. Now I'll put this value of xn in the formula of xz. So I'll get this term. Now we know that the summation of the sum is same as the sum of the summation. That means I can separate the two parts. Now here A1 and A2 are constant, so they can be easily taken out of the summation sign. So A1 summation x1 n z raised to power minus n plus A2 summation x2 n z raised to power minus n. Now if I will consider this part of the summation, this is actually the formula for Z transform of x1n, which we have already discussed. It is x1z. Similarly, this part of the summation is the formula for Z transform of x2n, which we have already taken as x2z. So we will write x1z here and x2z in place of this summation. So this is the final Z transform. So this is the property that if the signal is this, then the Z transform will be this. Now the ROC will be the intersection of the individual ROCs of x1z and x2z. Now coming to the second property of the Z transform, which is time shifting property. Now according to time shifting property, if I have any signal xn whose Z transform is xz, then if I shift this signal in time domain by k units, say, so the signal will be xn minus k. Now, the Z transform of this shifted signal will be xz but multiplied by z raised to power minus k, where k is the number of units by which this signal is shifted. And the ROC of z raised to power minus k xz will be same as that of xz, except for z is equal to 0 if k is greater than 0 and z is equal to infinity if k is less than infinity. Now, coming to the proof of this property, now we will start with the left hand side, which is the Z transform of xn minus k. Now writing the formula of Z transform, n is equal to minus infinity to infinity, signal and z raised to power minus n. Now here the signal is xn minus k, so I have written xn minus k in the place of the signal. Now here I can manipulate the term. What I have done, I have multiplied this term with z raised to power k and z raised to power minus k. We know z raised to power k and z raised to power minus k, this product gives 1. So it doesn't make any change to this term. So z raised to power k will be merged with z raised to power minus n, where I have taken minus common. So here it will be n minus k, and z raised to power minus k will be outside this z term. Now, since z raised to power minus k is independent of n, so it can be taken out of the summation sign. So z raised to power minus k is out of the summation sign, in summation n is equal to minus infinity to infinity x n minus k z raised to power minus n minus k. Now I'll put n minus k as m. So here I'll put m and m in place of n minus k. Now since I have changed the variable, the limits will automatically change according to the substitution. Now n minus k I have taken as m. So if n is minus infinity, m will also be minus infinity. If n is plus infinity, m will also be plus infinity. So this will be the now new variable limits and xm z raised to power minus m. Now if I'll see this summation sign, this is actually the formula for the z transform of signal x. And we have already discussed that this z transform is xz. So z raised to power minus k xz. So this proves the property that z transform of x n minus k is z raised to power minus k xz. Now similarly, if I advance the signal by k units, which is x n plus k, it will be z raised to power k xz. Now coming to the third property, which is scaling in the z domain. Now, if I have any signal xn and its z transform is xz, and the ROC is between R1 and R2. Now, if I multiply this xn with a raised to power n, then the z transform will be xz divided by a. That means z will be divided by a. And there will be change in the ROC also. Now, instead of z between R1 and R2, now the z will be AR1 and AR2, where A is a constant which can be real or a complex. Now coming to the proof of this property, I'll start with the left hand side, which is z transform of a raised to power nxn. Now first I'll write the basic formula for the z transform of xn, which is xz is equal to summation n is equal to minus infinity to infinity xn z raised to power minus n. Now instead of the signal, I'll write the signal for which I want to find out the z transform, which is a raised to power n xn z raised to power minus n. Now here we have a raised to power n and z raised to power minus n. So I can combine these two terms by taking power n as common. So here it is xn a raised to power n z raised to power minus n. So here I have taken minus n common, it will be a inverse z. Now if I'll see the summation sign, this is again the formula of the z transform of xn. But in case of z, instead of z, here we have a inverse z. So instead of writing xz, I will write it as xa inverse z. And xa inverse z can be written as xz upon a. So this is the property which we wanted to prove, that the z transform of a raised to power n xn is equal to xz upon a. Now this is all for today's lecture, and in my next lecture I'll discuss the remaining properties of the z transform. Thank you.